pleasure to be here and share some of the excitement we've had in the past 5 years in understanding the Milky Way galaxy and asking very deep questions about ourselves, where do we come from, and the nature of our universe, what it is made of. And so these are kind of the two main questions that I try to answer in my research. And probably many of you could kind of, when you boil down to what you're answering, this is something very similar. It could be those exact two questions. So the way I'll be tackling this is in the context of the Milky Way galaxy. And this all happened thanks to the European Space Agency's mission Gaia, which really transformed our view of the Milky Way, that for really millennia was something like this, a static view of positions of stars that we can see in the sky, and maybe measure their colors or spectra and get some additional information. But really what triggered this revolution that we are experiencing today is the measurements of the 3D motions and 3D positions of stars throughout the galaxy. And so here is a movie that really visualizes this kind of forward evolution from the Gaia data release 2, where we see that now that instead of just like having the static view of the Milky Way stars, that we can actually integrate their orbits forward and backward in time. And this view of their present, not just the present, but also the past orbits of the Milky Way can tell us really about where those stars come from and how they got here. And this is a very striking visualization of something like 60 million stars, but it is really only the brightest stars that are very close to the position of the sun. And so what I'm interested in is actually discovering the nature of the whole galaxy and making this experiment basically throughout from not just the position of the sun, but all the way to the edge of the galaxy. And to do that, we need those 3D positions and the 3D velocities that unfortunately Gaia will only provide for the brightest of stars. So this is the reason why a group of us at the CFA started the spectroscopic survey called H3, which stands for Hectoshell in the Halo at High Resolution, where we were complementing Gaia observations and measuring spectra of stars kind of fainter than Gaia will observe, so between 16 and 18 magnitude. And so here is kind of our targeting strategy. So starting with Gaia as the input catalog and selecting stars that are farther away or have a parallax smaller than 0.5 milliarc seconds. We've been putting hectoshell spectrograph fields on these high latitude regions of the galaxy. You can see as time goes on, we've been kind of filling out this footprint in a fairly uniform fashion. And today we have basically observed most of the stars that is still visible from the northern hemisphere, where the telescope is situated in this kind of galactic, southern galactic cap, and are making our way through the northern galactic cap as we speak, basically. And so every pointing here has, so it's a fiber-fed spectrograph that has 200 science fibers in every pointing. And we have been observing in this very small wavelength region around the magnesium B triplet that has these very strong magnesium lines at a very high resolution of 30,000 and which this then enables us to measure radial velocities very precisely. So we've been kind of tailored our exposure times to have signal to noise of 3 for our faintest stars, and this still allows us to get 1 kilometer per second radial velocity precision for basically the entire of our sample. So this has been a way to complement Gaia information. So instead of just having Gaia to the positions on the sky and the proper motions, now we have the radial velocity as a kind of the fifth phase-based component. But this, as I wrote here, we have this spectrophotometric analysis. So not just taking the spectral information that we have been gathering through the survey, but also combining it with the existing broadband photometry. And Phil Cargill here, who is a postdoc at the CFA, wrote a pipeline that simultaneously fits both the spectrum and this broadband photometry. And the reason to do that is that we can then take advantage of the temperatures and surface gravities that we measure from the spectra, or can constrain from the spectra, and get a better sense of the total luminosity of a star from the broadband photometry. And so in a sense, this gives us an estimate of the total luminosity and therefore the distance to the star. And even though this is not impressively precise, it is much better than Gaia parallaxes, especially in the outer halo. So the precision in distance we have is something like 20%. And so now, having completed all full 6D information, we can kind of make the same movie of H3 stars. So starting with some of them colored here by distance, I'll play the half a billion years into the future. You can see that we have, so these are all distant halo stars, and some of them are very distant at tens of kiloparsecs away. And so the very first thing that we did with the survey is estimate what is the total amount of mass in the galaxy from the motions of these stars. So this is the first paper by Dan Zaritsky, put just a lower mass limit to the Milky Way of being 0.9 times 10 to the 12 solar masses. And then a couple of years later, we had a paper Jeff Shen actually constraining the total mass of the galaxy to be something like 10 to the 12 solar masses. And this is very exciting because obviously if we kind of account for all of the stars that we know, it's a kind of a factor of 10 lower. So we are really probing these dark matter dominated regions of the galaxy, especially, and providing very strong constraints in this outer halo regions. Another interesting thing that you might not have expected, but can kind of clearly see here, is that the orbits of these stars that I've really just randomly sampled from our catalog are not random. So there appears to be some structure to this, and this is probably the most prominent one. It turns out when we kind of trace these orbits back, you get to the Sagittarius dwarf galaxy. So this is, I'm showing here a view of the sky coordinates on the top. So they have the galactic latitude on the y-axis and galactic longitude on the x-axis. And so the galactic midplane would be at latitude of 0, basically. And so the light points are from Eugene Vasilyev's work when he kind of just took the Gaia data, starting from the Sagittarius dwarf galaxy and kind of following the tidal tails emanating from it. And so you can see those are the lighter points. And then the darker points are members selected by Ben Johnson using H3 data, where the selection was made purely on the angular momenta of these stars. And so when you look at it, it looks like there are some maybe stars that are offset from the main track identified with Gaia data alone. And this becomes particularly obvious in the bottom panel, where I'm showing radial velocity as a function of galactic longitude, where there are like a number of stars here at more positive radial velocities that appear kind of to be maybe even contamination in our model. But when we actually compare this to the model that Eugene ran of an n-body simulation showing the disruption of a Sagittarius-like dwarf galaxy in the Milky Way, it looks like that these actually, the model predicts an older wrap of Sagittarius, right, to have these radial velocities at these galactic longitudes. So the model is now shown in these shades from black to yellow, with the yellow being stars that were stripped from the Sagittarius dwarf galaxy in the like the furthest back in time. And so it looks like that indeed our selection, just based on orbital properties, is actually finding these very long ago stripped stars, and maybe provides a hope that we can, in this way, kind of disentangle the full accretion history of the Milky Way, and in this sense kind of ask this question, where do we come from, or which are all of the galaxies that came into the Milky Way to form our galactic environment as we have it today. And so to move in that direction, I will here visualize actually a beautiful idea suggested 20 years or more than 20 years ago by Amina Helmi of actually finding very old merger events in the Milky Way or any galaxy by not looking at the kind of observed coordinates, but actually in the phase space. And so here on the left-hand side, I'm showing a Milky Way-like galaxy with a disk and the position of the sun as a star. And then I'm showing a model of a dwarf galaxy disrupting in the Milky Way potential. And as you can see, that tidal forces of the Milky Way are shedding the galaxy, pulling stars apart into these very long stellar streams. And as time goes on, like this also mixes and becomes part of just our stellar halo. And as we have more galaxies shown here with different colors, everything kind of gets mixed together. So if we didn't really have colors to tell them apart, it would be actually hard to say which star came from which galaxy. But this is only if we are looking at this in the kind of configuration space. And if we look on the right-hand side, in the space of energies and angular momenta, we see that these galaxies occupy different regions of this space. So this is basically the proposal from Amina, her collaborators, that we should, if we are able to calculate energy and angular momentum, or orbital energies and angular momenta of stars, we should be actually able to map out where they come from and search for overdensities in this space, or rather saying that the overdensity in this space would correspond to a unique progenitor of the Milky Way. And so this idea seems really nice and simple. It really just kind of relies on the basic physics theorem, or Noether's theorem, that conserved quantities provide a symmetry in space. However, calculating these quantities is hard, and that's what took basically 20 years to be able to do, because to calculate the angular momenta, we need to like those 3D positions and 3D velocities, and in addition to calculate energy, we need all of that, and also some model of the gravitational potential of the galaxy so that we can calculate the potential energy. However, now we are at the point where we have a pretty good guess, at least on average, what the Milky Way potential is like. And as you saw, we also have these measurements of the positions and velocities of stars. And so without further ado, here's work from Rohan Naidu showing the space in the H3 data, basically. And as you can see, this phase space diagram actually looks pretty structured. So we have most of the halo stars here at angular momentum of 0. Like there's this big cluster which was identified. Was basically one of the first science results from Gaia that came, that saying, well, this is the most massive merger that happened in our galaxy. Then another one, the Sagittarius galaxy that we just saw, is part of this structure over here. And so those are the two main structures over here. But what Rohan did was kind of isolated those and look what else is there, and found that basically for 85% of the stars in our sample that he could identify the unique progenitor here. And so this was very exciting finding, that we actually can decompose our galaxy into its individual progenitors. And at this point, we kind of have seen what are those sort of two frontiers that are opened in our Milky Way halo. The one side, we have this view into the very first galaxies that were kind of born a very long time ago and accreted on the Milky Way and basically preserved. So we could study their chemical properties, like ages, to learn really about these earliest galaxies in a way that we'll never be able to do directly by observing them, say, with space telescopes. On the other hand, we have the frontier of dark matter. This is the dark matter dominated region of the galaxy. We have now a lot of tracers. And this is the part of the work that I am most excited about, and I'll be talking about throughout the rest of the talk. But I'm also happy to chat more about the first galaxies and what we'll learn about that after the talk. So the reason why I'm excited about studying dark matter in the Milky Way is that this is our galaxy provides us with basically a laboratory for dark matter. And despite all of the different ways people have tried to study dark matter that have not been gravitational, like the direct detection experiments, this you have only led to non-detections so far. And really the only positive signal of dark matter has been gravitational. And so this is why I think it's important to look at what different models of dark matter would predict in an environment like the Milky Way. And so the figures here show 3 different cases of dark matter models. So the standard dark matter, cold dark matter model, where dark matter is a weakly interacting particle of the mass on the order of GeV, is shown on the left. So we see that in a Milky Way-like galaxy, it should be surrounded by a number of these smaller clumps of dark matter, so-called subhalos. However, those are predicted to be completely dark, and we haven't seen them yet. So it's a question of like, do they actually exist, or is maybe dark matter something different? For example, a lighter particle on the order of, with masses on the order of keV, where yeah, the overall distribution of dark matter is pretty similar, but just those very lowest mass subhalos don't exist, as shown in the middle. Or it could be something entirely different, so a particle mass of 10 to the minus 22 eV. And in this region, yeah, we also don't have this substructure, but instead the whole of the distribution is some sort of dominated by quantum mechanical turbulence on these astrophysical scales that actually changes a lot as a function of time. And so the difference between these 3 models is well established theoretically, but kind of to test it observationally, we really wouldn't need to have a precise tracers in these outer regions of the galaxy. And this is why I'm excited about, because it turns out that kind of nature has given us these a very precise gravitational antennae to try to distinguish between these scenarios. And maybe they come from an unexpected source, being the globular clusters. So show here an illustration of a globular cluster orbiting the Milky Way, and due to 2 body interactions within the cluster, kind of ejecting stars or evaporating stars, basically that follow very similar orbit to that of the cluster itself. And as stars leave the cluster, they kind of barely just make it out, which means that the following stellar stream or tidal tails that form is kind of very thin and kinematically cold. And this is the property that, in particular, these tidally dissolving globular clusters, what makes them really useful for tracing the gravitational potential and kind of how bumpy it is. Yeah.
So I was going to ask, how important are the interactions between the cluster and the disk, especially the gas disk, because it's passing through this yellow disk in your simulations?
Yeah, that's a great point. It's and this one actually is to scale. So this is a model of an actual stream that you'll see like in a few slides, called GD1, and the disk is to scale. So we think this stream in particular is better suited for studying the dark matter, or to put constraints on dark matter, because it actually only passes through this in this very outer region. So this is at so the pericenter is at 13 kpc, where we think that there shouldn't be much disk shocking. But yeah, there are some other streams where that definitely does make a big difference. In particular, PAL5. Some of the early work actually has shown that this is basically what led to the cluster being disrupted so quickly, because it was puffed up and then able to lose stars more quickly. Yeah. So yeah, indeed, the streams are kind of agnostic of what sort of gravitational perturbations they're sensitive to, but as you can see that they do orbit, or some streams at least orbit in the halo, so they have the chance of encountering dark matter subhalos. And kind of what happens in the absence of subhalos is that you, in a completely smooth galaxy, is a stream that looks like this, kind of a one-dimensional structure. However, if we put it in a same overall gravitational potential that has a cosmological kind of live dark matter population of subhalos interacting with the streams on this orbit, is a stream that kind of on average has the same position as the one the one on top, but it has a lot of these density variations along the stream. So there's an overdensity and then a gap or an underdensity, and some stars kind of scatter out of the stream. And here on the left, even a part of the stream that looks to be kind of completely detached from the rest of the stream. And so this has become the experiment that we as a community want to make here, to observe stellar streams in the Milky Way and see whether they're more like the one on top, or if they have evidence of these encounters with potentially dark matter subhalos as well. And so for a while, well, we were at first just excited to find streams. So this is a view of the SDSS North Galactic Cap, so a density map that kind of maps different color channels to different distance bins, and selecting old metal poor stars that are more likely to be kind of globular cluster stars. And so you can see that it reveals a lot of substructure in the halo. Like these broad spots are the globular clusters and still bound dwarf galaxies. And then this most massive diffuse feature here is the Sagittarius dwarf galaxy, or the tidal tails from the Sagittarius. And this band to the right is an orphan stream, which we think is also a dwarf galaxy stream, just lower mass than Sagittarius, because it is slightly less wide. But we haven't found a progenitor dwarf galaxy, so that's why it was called orphan. And the streams that I'm most interested in studying are the one that look kind of like this. So here in the bottom left is the globular cluster Palomar 5, and it has two tidal tails emanating out of it. And so you can see that these are much thinner than the dwarf galaxy streams, which we think would make them more sensitive probe of gravitational potential. And the stream that I'll be talking about most is the one that I already mentioned, called GD1. So it starts here at the bottom right and kind of goes to top left. But yeah, hopefully you can see it from the back as well. And it's kind of faint, and that has been part of the problem, because when you look at the kind of in detail, you might see like, oh, maybe there are like some parts that are denser than the others, but it's actually really hard to tell, and it's not just a projector; it's an actual limitation of the data that because we only had colors of stars to determine whether a star was a member of the stream or a member of the kind of just field population of the Milky Way. It was actually hard to tell what the origin of this density variation are. But then this is kind of where Gaia really changed this a lot. And just kind of a historical note, this is a work that Adrian Pricewell and I did right at the morning of the data release of the second Gaia data release. And so we knew that GD1 was this stream that was fairly long. It was kind of nearby, and we said like, okay, let's just go check out what it looks like in Gaia. So we selected this region of sky. So these are sky coordinates phi 1 and phi 2. And the streams should be aligned along phi 2 equals 0. So the first selection we made was just on parallax, so to select stars more distant than 1 kiloparsecs. And when you look at that, nothing really shows up, or rather you just see kind of there a little bit more stars to the left end, which is kind of where we are getting into the Milky Way disk. But then when we just do, why is this flickering? Okay. When we do just one more selection to apply proper motions to be kind of retrograde along the stream, like in basically in the opposite direction from the galactic rotation, you can already see individual stream members popping out. And so this is already way better than anything we had before, because before we had to kind of pin all of the data on sky and kind of had some membership probability. Here we have individual measurement, individual stars that we can point out to be as members. But then we also haven't even made use of that color information that we have. So if we applied an isochron selection, kind of having these stars to be consistent with an isochron at 8 kiloparsecs and metal poor, we get a really clean map of the stream. And so that you can get a sense of kind of what the background contamination is from top and bottom fields. And so if we just kind of calculate what is the excess probability of these stars, assuming a uniform background, we get a model that looks like this. And so this figure now looks kind of like what we were hoping to find, is that there would be substructure in the streams, that there looks like there's one gap over here, another gap over here, and even some stars that maybe like even though they were kind of predicted in the field, but like people really mostly focus on finding these gaps, but we also find these kind of stars off of the mainstream track. And we thought that these are actually very interesting. And then after quickly writing up this paper, spent a few months modeling this feature over here, having wondering if we can reproduce the gap and the spur feature in an impact of something like a dark matter subhalo. And it turns out that actually we can. We found a good solution. So here is a model of GD1 stellar stream encountering a dark object or compact object that kind of gives a velocity kick to stars that kind of change their orbit and then precess around their original orbit of along the stream. And when we kind of zoom at the present day, we see that the distribution kind of has this underdensity closest to where the encounter happened and has this spur of stars displaced on the side of the stream. And so if we project them in the same sky coordinates and show the data, observed data on top and the model on the bottom, we see that they actually match pretty well. There's this kind of gap around 10 degrees or 8 degrees wide, centered at minus 40 degrees. And then this has this spur of stars extending for another kind of 10 degrees and offset by a couple of degrees from the stream. And the exciting part of this model is kind of listed here in the left. It was showing what are the parameters of the impact. So it happened something like 500 million years ago when the mass of the object was 5 million solar masses. So if this was a dark matter subhalo, and this would be basically showing that being the first convincing evidence that we have this empty dark matter only subhalo with no stars associated inside it. And then here the properties, it's on the size, it seems like it's 10 parsecs, and then impact parameter and velocity of impact. And so, of course, this is just kind of a proof of principle that you can get something like this. We wanted to get a sense of kind of how well these parameters are constrained given this data that we have. So we checked it for all of the parameters, but here I'm just showing the mass and the size. And so the constraints are not not the greatest. So it's still a pretty wide contour. So the gray shaded region shows where the region where we found models that are consistent with this data that we have at the present. So overall, it is a range of masses between 10 to the 5 and 10 to the 8 solar masses, but all fairly compact. And when we compare this to the known objects that we know in the Milky Way, it's kind of more compact than most. So the circle shows molecular clouds, the squares are dwarf galaxies, and the triangles are globular clusters. And dark matter subhalos would be in this band. So this is the lambda CDM prediction for where the subhalos should be. And the dotted lines show the 1, 2, and 3 sigma kind of scatter around the mean relation. And so kind of looking at face value over this, you say like, well, then clearly it must have been a globular cluster that in fact it has like this largest overlap with the allowed region. However, what Gaia allowed us is to calculate orbits of clusters back in time. And then by doing that, we found that none of the clusters, nor dwarf galaxies actually, came close enough to the stream to actually be able to make this sort of signature. So then we are kind of left with a puzzle. It's like, okay, maybe it's a globular cluster we haven't seen because it's, I don't know, maybe hiding on the other side of the disk. Could be. We think like we have discovered most of the globular clusters, but in principle, they structurally fit the bill at least. Then another option would be that maybe it is something an unusually dense dark matter subhalo. Or something else that's very dense. So our solutions are perfectly fine with this being a point mass object like a supermassive black hole. Of course, there are not many reasons to expect supermassive black holes to roam around in the halo, but we're trying to be agnostic here, and kind of try to take a next step and see how can we tell. Was this a question?
Finish your sentence first.
Oh yeah, go ahead.
So supermassive black holes, how big are supermassive black holes?
Yeah, we never pushed it very, very hard to see if we can have like 10 to the 4 solar masses. So definitely 10 to the 5 would work. And
so, yeah. On the modest side.
Yeah, it wouldn't have to be like very supermassive. Yeah.
While I'm interrupting you already, so when you show the screen in shaded areas, what is actually uncertainties and error bars on this? Is it possible that within 1 sigma it still matches and there's not a real problem?
Oh, like with this band, yeah, that's a, yeah. It really, the reason why I didn't put contours is that we don't trust our modeling to be able to reliably give us a sense of probabilities, because we had a very idealized likelihood to in how we described basically how we evaluate the encounter. So yeah, if I put it here, so the metrics we use was basically to just have a gap at the right position and of the right size, and also to have like this track follow the observed track of these spur stars. But in principle, I think there should be a lot more information that we can get if we actually calculated the relative densities both in the gap and of these spur stars. So because we didn't do that, we didn't fully believe like any kind of likelihood, even though we did calculate it. I plotted here just the kind of contour of what looked like plausible models. Yeah.
Thank you very much.
Of course, that's a great question. Yeah, and yeah, I'll just to kind of explain like why didn't we do that? We never actually believed like we would be able to do things like that. And it really comes down to having both of these features, the gap and the associated spur. So all of the theoretical analysis before this data was available was focused on extracting information about the encounter just from the gap, the size of the gap. But that on its own is very degenerate with kind of the time of the encounter and the mass and the velocity. So it was always like the status of the field was, the expectation was that we'll like need to detect many of these gaps to kind of get some statistical view of the total population, and not really focus on one single object to try to decompose the merger, basically. So it was, yeah, we're in swimming in uncharted waters here. Yeah, but given that like now we have that, we are like wanted to go even further ahead and say like, okay, well, you know, assume that like this does work, that we actually can analyze a single encounter. We can take all of these models that kind of are plausible over here and ask, where will this progenitor, the impactor object, be today on the sky? Could we go look out and find it, and then just, you know, if we see a globular cluster, be like, well, I guess it's a globular cluster. Unfortunately, when we took those models and predicted where they are on the sky, it can be literally anywhere. But the color coding here of these different kind of solutions is by the relative radial velocity that they would impart onto the stream between the kind of main part of the stream and that spur part. And you can see that there is some information about it. There's some that hopefully if we measure this difference, we will be able to further constrain this. So this is exactly what we did with a follow-up spectroscopy. And we found that basically the stream and the spur are almost co-moving. So the relative radial velocity was smaller than 1 kilometer a second. And this constrained, or rather rule out many of the models, but still, yeah, it's not a LIGO level localization. There's still like thousands of square degrees on the sky, or kind of covering the plausible models. So we're hoping to do even better by measuring more precisely relative proper motions. And so here I'm color coding by proper motions, and we have an HST program with the second epoch being taken in actually just a few months in February of 2023, where hopefully we'll be able to further limit this. And what we are hoping to do this with with this kind of analysis is then compared to some known sources. And one example, collaboration I had with Mr. Mirabal was to cross-match it with Fermi unclassified sources that had, so Fermi, from Fermi Gamma Ray Telescope, to compare to sources that look like they may have a spectrum like what you would expect from dark matter annihilation. And so those are the sources shown in blue, and now there's a number of them. Like the distribution is a little bit not small enough to allow any concrete solutions, but I think it charts the way into the future if we do better in constraining this from gravitational aspect, that we might actually be able to study well, if we have a detection of a dark matter subhalo, actually to have some multi-messenger aspect to the study as well. And this is kind of where the direction we're hoping to go with this particular object, but then kind of going back to this question of what do we learn about dark matter overall, and actually convincing ourselves that this is dark matter subhalos, we should actually expect signatures like this in outer stellar streams. And as people have started looking at different streams, we actually have been finding different signs of perturbation. So here I'll just cycle through a few of them, starting with Jalem stellar stream, which appears to have a very thin component and then a wider kind of envelope around it, which is unexpected for a globular cluster stream. Like it should be really just kind of a one-dimensional thing. It is definitely looks like a two-dimensional structure. Then we have the Palomar 5 globular cluster. Now this is actually taking into account it's based on data from the dark energy camera. So the stream is at a distance of 20 kiloparsecs. So the mapping it with Gaia alone is actually pretty hard, but we're showing here that even just having deep photometric data, that we can reveal density variations in such a more distant stream, showing that, it looks like there may be a gap over here and maybe a gap or under density over here. And then also the width of the stream changes. So there's it's much thinner on the trailing side on the top than and it seems to fan out at the bottom on this leading side a lot, which again is some sort of signature of some sort of dynamical interaction with at least something in the Milky Way. And then finally, I have this interesting case of what we originally thought were two stellar streams called Alika Uma and Atlas, but when Tingley went to measure radial velocities with S5, part of S5 survey, which is, as you know, is here at AAT, found that actually they have consistent radial velocities and appear to be part of the same structure, and this break is some that kind of spur feature that we were seeing in GD1. So it looks like there's a number of these structures, and so now to get back to the question we started from, initially the really big or the main question of the field is now identifying what is the origin of these perturbations. Is it something external, like this encounter with a dark matter subhalo that forms a gap, or is this due to some internal process, like what was predicted a couple of years ago, that if globular cluster starts losing star in a dwarf galaxy before it merges into the Milky Way, it might end up with this kind of wider envelope and maybe form some of these spur-like structures as we are detecting in the data. And so to kind of disentangle these options, what we'd really like to have is accurate orbits so that we can kind of rewind objects back in time and also identify kind of what their origins were, whether they were born in a dwarf galaxy or were just kind of, or how long they have been in the Milky Way. And this is kind of a little bit complicated by the by the fact that at least for this level of precision, we would really like to have accurate orbits, and we know, but because of all of these mergers, we don't expect the gravitational potential to be very simple. And so here is actually a prediction based on a simulation from Nico Garavito Camargo of the Large Magellanic Cloud encountering or being folded into the Milky Way. And so the contours show the expected dark matter halo distribution of the outer parts of the Milky Way. As you can see that there's this kind of wake along the orbit of the LMC where the kind of stars are kind of drawn by the LMC, and on the other end of the galaxy there's this so-called global response, which corresponds to the change in the center of mass of the galaxy just because of this very massive dwarf galaxy coming into it. So this is this was theoretically predicted, but already there seem to be indications that, at least in the stellar component of the halo, the similar anisotropies actually exist. So here is a map of K giants in the distances between 60 and 100 kiloparsecs from the sun, so very outer regions of the galaxy. You can clearly see that there is this wake component kind of following the path of the Large and Small Magellan Cloud, and there's another overdensity of these stars on the other side of the galaxy. So it does look like the potential of the Milky Way is not trivial. But you might, anyway, at least my hope for a while was that maybe this is, just something that is happening in the outer galaxy due to LMC now, maybe like in the inner galaxy where we have most of the streams, this is not as much of an issue. But it turns out that even though it's, if it's not as complex, it was definitely not a spherical halo in the inner galaxy either. And an indication showing that is over here, illustrated in what Yuri and Belokharov here shown is the distribution of the stellar halo. It seems to be in the inner galaxy that it is in an ellipsoidal shape that is kind of tilted with respect to the galactic plane. And Jesse Han, who is a graduate student at Harvard, also had a paper showing that in order to preserve for a long time, for billions of years, this structure, like this tilted stellar halo, actually requires a tilted dark matter halo as well. So this movie I will play here will show kind of how stars evolve in two gravitational potentials, and the left-hand side will be like a tilted dark matter halo following kind of the shape of the stellar halo, and on the right-hand side will be the will be the spherical halo. So you can see that if dark matter halo were spherical, that like the structure, the tilt of the stellar halo would be erased basically after a gigayear, whereas in a tilted halo it is preserved, showing basically that even the inner parts of the galaxy that we thought were maybe assembled a long time ago actually may have kind of some record of this asymmetry due to the hierarchical buildup of the galaxy. And so this all kind of makes it seem that it's really answering the question of the origins of the galaxy, and the very precise underlying gravitational potential may be hard. But I think there is a way forward, and it comes from analyzing stellar streams together as a population. And I'll show here another diagram of energy and angular momentum phase space. In the background, we still have H3 stars. And this is my kind of Gaia EDR3 project, where I thought that the proper motions were a little bit better constrained, especially in the outer galaxy. And we were for more distant stars, and including many of the streams. And so then, in addition to showing just stars, I was able to put orbits of stellar streams in this diagram. And what we found after we did that is that they seem to be clustered over here. We have some streams, kind of a group on the right-hand side, and then 3 groups on the left-hand side. And what this signalizes to us is that it looks like that we actually are finding streams that were accreted together as a part of the same dwarf galaxy. And in this way, basically can find those that were actually born in individual dwarf galaxies and find their origins this way. Another thing that came out of this paper is that after kind of plotting the stars in this diagram, we saw that some of them lied very close to the known globular clusters. And when we integrated orbits from these globular clusters, back or forward in time, depending on the cluster, we saw that they actually match these or a number of these stellar streams. And this was really puzzling because we expected the streams kind of to connect all the way to globular clusters, but for a number of them, yeah, they just don't. So it's definitely a puzzle of how that happened from the dynamical point of view of the globular cluster evolution, but in a more kind of utilitarian sense, this actually provides us a very sensitive handle on the gravitational potential, because we know that these stars, and that we checked metallicities of, that they have the same metallicity as the, say, globular cluster. We know they had to kind of come out of it. So having these stars that are hundreds or 100 degrees offset will put very strong constraints on the underlying gravitational potential, and hopefully we'll be able to start mapping those very weird and asymmetric shapes that are predicted. And so the road forward is basically to kind of do more of this and analyze all of the streams that we have in the Milky Way in this joint framework. I'm here cycling just through 20 or so that have orbits constrained at the moment. You can see that they have different orientations and different galactic-centric radii, and therefore different regions of the galaxy that they explore. And so what we are really hoping to do is have a uniform sense of these stellar streams and kind of analyze them in a similar way. And part of this is hopefully we'll achieve at a community meeting in a couple of months called Streams 22, the Community Atlas of Tidal Streams, where we'll hopefully be able to compile all of the data that we have on stellar streams and kind of open up to the community to study in this uniform fashion. So I'd love to chat with all of you if there's any interest in our data that you have that we can fold into this catalog as well. And with that, I'll end and take any of the questions you might have. Thanks.
So I was just wondering if you can ask the question the other way around. So you're talking about looking for perturbations in the stream, but how many, I mean, can you say why the stream is so thin? Is that plausible given the number of dark matter halos that you expect in the Milky Way?
Yeah, that's a really good question. Actually, I was working with a student a couple of summers ago, where we were measuring velocity dispersion in the GD1 stellar stream, where we have the best data, and it is on the order of 2 kilometers a second. So it is fairly cold, and we could what we were hoping to do is actually put a constraint on this on these so-called fuzzy dark matter models. And turns out, it's very constraining. It kind of like I think the most popular one is on the order of 10 to the minus 21 or 22, and that would actually be provide much more heating than what we see for this particular stream. So I don't know if there are any kind of modifications. Obviously, like it could be kind of a little bit more massive, but then I think it's not as exciting model for explaining other observations. So yeah, indeed, that actually does provide a pretty strong constraint overall.
Can you distinguish between the pictures on the left, for example, based on, or say, for example, even if you took your Fermi, you say that they're all dark matter subhalos, what's the probability of having a stream still intact and thin?
That's a great question, and initial work has kind of assumed, it was purely analytical, where we took just a kind of radial profile for what we expect the number density of subhalos to be at different radii of the galaxy, and then just took the average orbits, and for the stream like GD1 in the past 8 gigayears, I think it should have had between 1 and 2 encounters that we would detect. So from that perspective, we were like, okay, this kind of checks out. We have 1 or 2 prominent gaps, but I think this prediction is actually overdue a revamp, taking into account this more realistic distributions of both orbits and also the, well, orbits of streams and orbits of subhalos. And I kind of really started thinking about this more after seeing this picture over here, kind of how specific it seems like all of the streams are, or subhalos that could have interacted with GD1 follow like a same orbit. It looks like it's a great circle on the sky, and yeah, I didn't put it here, but it coincides with the orbital plane of Sagittarius dwarf galaxy. So it made me think, well, if it's something that came in with Sagittarius, then some streams that were kind of more aligned with Sagittarius would have a much higher likelihood of being, having had an encounter than some other streams. So I think a better theoretical study of kind of what the expected number of streams, or for different streams is, needed at the moment. Yeah. Mm-hmm. Oh, good. Yeah. Go ahead.
Right here, please.
So I actually had a question about this slide. The relative velocity of the perturber seems quite low. And additionally, you mentioned a moment ago that the velocity dispersion within the stream GD1 was only 2 kilometers per second. I'm very surprised that we have. I might expect that the perturber would still be in the stream. Why is it so slow relative to the stream? And now, I guess my question is, can we rule out that the perturber is part of the stream and not some tertiary?
Yeah.
Will repeat the questions from the.
Oh, yes. Sorry. I guess the question here was about the small relative velocity here we have measured, and whether it was whether we can rule out that the perturber was part of the stream or the system rather than something external. So yeah, one thing to clarify is that this is the relative radial velocity between two different parts of the stream, and not the stream and the subhalo at impact. But I think it is a good question whether, and before kind of this insight of thinking that maybe these all are structures that came in on on kind of more coherent or correlated orbits, I would have said like that it would be a very low likelihood that you would have something that was kind of part of the system. But now it actually, I think it is worth calculating this probability more strongly. So in our setup, we just assumed like we didn't assume anything. Like the way we parameterized it was kind of at the time of encounter. We had kind of the time when it happened, which kind of set part of the stream, and then the 3D velocity and the kind of offset from the kind of what the impact parameter was. So in principle, I guess we could have found solutions that were kind of co-moving with the stream. We didn't really find it, and okay, maybe let's see. Okay, if I can quickly shift to some backup slides. Okay, so here, like this is just like a little bit of an exploration, kind of what happens when we change one parameter at a time. So I'll be focusing here on the kind of relative velocity between, so this is now the relative velocity between the stream and the subhalo or the object at the impact time. It looked like for the very low relative velocities, which would be something that is kind of more co-moving, that it is hard to actually form the exact shape of the gap and the spur of stars. But we also didn't, this is just kind of what kind of came out from this very agnostic analysis. I think it would be worth actually, constructing an experiment that tests this in more detail, especially given that now we have like a good motivation to do so. Just on a side note, GD1 does look like it is on a retrograde stream, and we know that there have been retrograde mergers as well. So it might be that it actually has interacted with something like that came together. Yeah.
Thank you. I love all the videos.
Oh, sure, thanks.
Any more questions?
Yeah, so maybe related to this question, I'm actually surprised by the very small relative velocities here, because I would have thought that you just have a much larger thermal component, right? Okay, if I look inside a globular cluster, right, its velocity dispersion of order 10 kilometers per second, right? Moreover, once in a while, I even expect stars to be ejected from globular clusters, ignoring tidal effects and so on. So velocities are 50 plus kilometers per second because of three-body interactions and things like that. So why is the bulk velocity so narrowly confined, given that I expect as effectively a thermal velocity that's an order of magnitude, 2 orders of magnitude larger?
Yeah, well, that's a great question. And we may even have streams that have like different signatures that may. Oh, sorry, I should repeat the question. Yeah, the question again was about the low velocity dispersion and how cold these streams are. So I guess maybe to first order, I could invoke the conservation of the Liouville's theorem, saying that because we are kind of spreading out in spatial coordinates, that we must get colder in velocity to kind of conserve phase space to kind of first order. And it could be that actually there are parts of the stream that are, well, that we haven't observed. So if you, just look at here. So these are all very, very thin and kind of cold parts of the stream. And we basically just targeted these parts. So you can see that, like, the issue is that we don't have radial velocities for all of the stars here, but just the ones that we targeted. So it might be that there is an envelope of stars that were ejected at a higher velocity dispersion, but that we are just seeing this kind of, or measuring this tip of the iceberg that we are identifying as the densest members. And so, because this almost spans 100 degrees side to side, and even if we have a degree field of view, we only get like 10 stars. So it's like very minuscule. But that's why I'm excited about like DESI and SDSS5, which hopefully will be able to reveal if there are any of these hotter components that they're not seen here.
Yes, maybe I can ask a question.
Yeah.
So when you go to the progenitors of the, when you have this plot of the progenitors versus like, I mean, what are your constraints versus the different clusters and and you showed only the cold dark matter, right? So would it be possible to try other types of dark matter as you showed, like the warm or the fuzzy, and kind of see where maybe they can fit on that figure? Yeah,
I do have not readily available, but I did actually a calculation for the fuzzy dark matter, the solitons. Because after kind of finding that the orbital plane is kind of similar to that of the Sagittarius, I was wondering if something like if it was a fuzzy dark matter model, then it would predict that there is a kind of a soliton core at the center of every kind of dwarf galaxy. And I was wanted to see kind of where that shape would be over here, and I think it kind of passes. Well, that's the thing. It like it depends on the mass, and so like for some range of masses, I think it passes through this region, but it might. I think it was maybe like slightly too high mass to be kind of 10 to the minus 19 or 10 to the minus 20. But that's a good question, and I actually got excited when I heard that there are some self-interacting dark matter models that actually predict a much higher dispersion, that they predict the possibility of much denser dark matter subhalos, and also some that are much more fluffy. But when I went to talk to a person developing that, he was like, no, this is basically lambda CDM. I guess he wasn't as concerned about the mismatch. So I guess on the data side, we would need to,
be more too practical for him.
Yeah, exactly. And maybe, as there was a question, in the back about actually having a probability aspect to the side to actually be able to kind of significantly rule out the lambda CDM sizes with some like high degree of confidence before kind of comparing to other models. Yeah.
There are no questions. I think we started 2 minutes late and we finished 2 minutes late, so I think we're good. So yeah, so let's thanks Anna again.
Thank you.